Okay, it is high time we come to terms with a little bit of reality. You see, we tend to trust doctors. We have a lot of respect for doctors. Heck, we've got Dr. Phil, Dr. Scholes. We even have Dr. Dre and Dr. Oz. Heck, we even got our favorite doctor, Dr. Capuano. And all these doctors get our respect. Well, I've got one more doctor you need to respect, and that is Dr. SARF. So, Dr. SARF may seem like a little too much, a little cumbersome, a little far out. However, Dr. SARF is the ticket to good health when graphing. So, I'm not going to fill this in for you right now. You're going to do this yourself. We're going to go over this with a blank version on the next page. Let's check this out. How does Dr. SARF work? We'll take any graph. Here's a graph. It's a kinematics. It's a verse time graph. It's changing with time. Let's make up a physical quantity. Let's make up a physical quantity called, let's call it Z. Or vector Z. What is Z? We just made it up. It doesn't matter what it is. And so Z has a little graph. Let's say Z's graph looks something like this and this. And if we really want to be approximate with it, let's just put a few times in here. So there's a time 0. Let's make this a 4, 8, make this one 12, 16, 20, 24. Okay, and say Z has values, has magnitude 0. We'll put here, we'll make this 5, 10, 15, and 20. So what is Z? Well, we don't even know. And the truth is, it doesn't even matter. What matters is that Dr. SARF makes house calls. And that means Dr. SARF will come through. Come on in, Dr. SARF. And whatever you need solved on this kinematics graph, Dr. SARF will take care of it. You see, Dr. SARF is very diligent, very deliberate, has a program, an algorithm that you need to follow. And it works like this. It's in order. The first thing Dr. SARF investigates is direct read. After that, if all is well, it goes to slope, then to area, and finally to rise plus fall. So let's see how this works. Direct read. Okay. Well, basically, if you get a question, for example, what is Z at 12 seconds? Well, you say, what do I want? Oh, I want Z. How do I get it from the graph? Well, plug in Dr. SARF. Let's see. The first thing we try is direct read. Do we directly see Z on the axes? Oh, as it turns out, we do. There it is. And so, you can directly read Z at 12 seconds. Z is 10. You could also do this in reverse. What is the time when Z is 5? Well, you can run in reverse over here. The time is 2 seconds. So direct read is just getting the physical quantities that are on the axes themselves. Okay, now imagine, replace this with instead displacement versus time, or velocity versus time, or acceleration versus time. Well, then instead of saying direct read gives you Z, well, direct read will give you displacement or velocity or acceleration. Fine. Now we also have this little loose. That's because direct read's a little more versatile than just looking at the axes. Direct read has a couple of subroutines. Direct read plus and direct read plus. Here they are. They are still based on just reading the axes. It's still something about Z or T. However, we can do a little more than just find Z at 12 seconds. We might, for example, want to know, find the average Z over 8 to, let's see, 12 seconds. Or let's pick one that's a little more interesting up here, actually. Let's pick 12 to 16 seconds. That's a little more interesting. Over 12 to 16 seconds. Well, what do we want? In this case, we don't want z. We want something very similar. We want average z. But it is still z, which you do see on the axis, which means it is direct read. You've directly read what you want on the axis. However, you need an average. Well, this is where we go back to our skill drill pop. You got to know your definition. Boom, boom, boom. Z, average. Do you know an average equation? Sure you do. In Regents Physics, we got our initial z plus our final z over 2. You may say, what is this craziness, this z? Listen, just replace it with a velocity versus time. And the question asks, what's the average velocity over 12 to 16 seconds? Oh, well, that's just the velocity at 12 seconds, there's 10, plus the velocity at 16 seconds, that's 20. 10 plus 20 is 30, divide by 2, that would be 15. So as a velocity, oh, it's 15 meters per second. An average velocity makes a lot of sense. The reason we're writing z is because you can do this with any kinematics graph. Okay, what's the other direct read? Plus. Well, you also might need something with z, but instead they might ask for the change in z. Maybe over the same 12 to 16 seconds. Well, it's still looking for z, which means on the axis, still a direct read, except now, change, delta z. Oh, delta z. Got to know that skill drill pop definitions. What's delta z? Well, delta anything you should know is your final z minus your initial z. The order matters. And so you could come over here and say, oh, 12 to 16. The final is 20. The initial is 10. 20 minus 10 is 10. Replace this with displacement. Replace this with acceleration. Replace it with anything. And all of a sudden, your change in displacement or acceleration or velocity, it starts to make more sense. So there's our direct read. Okay. Thank you, doctor. Now, if it turns out that direct read doesn't do it for you, and that sometimes happens, if, for example, they ask for something different, they may ask for something that calls on not direct read, but calls on an interaction of the axes where the z over t or the y over the x means something. And so after direct read, we always try slope. S is for slope. Well, slope is, by definition, your y-axis label over the x-axis label. That's what it represents. And this, again, got to know those pop definitions. The y-axis label over the x-axis label. And so if you get a question something like, well, z, we don't know anything, but I'll give you a different one. I might say, what is the average velocity over 0 to 4 seconds? Now, if this were, so this is on a d versus t. If this were a d versus t, you would take your d, the y label, you would take your t, the x label, like you did on the quiz today, and you would say d over t. Well, does d over t mean anything? Well, we have to then check. So in this case, it's actually z over t. Of course, z over t is make-believe, so it shouldn't be anything. But if it were d over t, you always go and check your PRT. In fact, now we're sticking to PRT 6. So, boom, PRT 6. Now you're not going to see z over t, we made that up. But if it were a d over t, oh, we would see that. Oh, it does represent something. Or instead, if it were a v over t, oh, that is here. That does represent something. Or instead, an a over t. Oh, wait a minute. You might have a little trouble finding that. Doesn't mean it doesn't exist. It just means it doesn't exist in our course. AKA, I'm not going to test you with a regular question on it. So over here, you find what it's equal to, and either it will be equal to something singular, or it will not. And if it is, boom, you're able to answer this question now. If it's not, then slope is not your answer. So, if we saw the physical quantity they're asking for on the axis, we had one of our direct reads or direct read uses. Next, if it's not one of those, you try out slope. Does this slope equal what the question is asking? So if this were a d over t, then this would be v, which does equal what it's asking. And then what do? You back up and do the slope. So if we pretend this is d over t, well then, slope from 0 to 4, here's your initial, here's your final, rise over run, rise of 10, run of 4, 10 over 4 would be 2.5. So if this were a dt, it'd be 2.5 meters per second is your average velocity because you did that slope. Okay, but slope doesn't always answer it. Sometimes slope is not the answer. But don't worry, the doctor's got more tricks in his bag. So direct read covered, slope covered. If neither of those answer the question, you might get a question instead, something like this. Maybe you'll get like question 5. What is the, let's say, distance covered? Or we could even say, what is the displacement during, use the same interval, why not? 0 to 4 seconds. And this one we'll do on a v versus t graph. Okay? Now, the next thing to try, if you were on a v versus t, and you were asked about displacement, well, the axes are v and t. Displacement is not a direct read, so that's not it. Next, you would try slope. And you would try v over t. Check your reference table. V over t is actually acceleration. So it is something, but it's not what we're looking for. So slope's not going to do it. The next thing to try is area. And area is always the y-axis label times the x-axis label. Now, what does this equal? Does this equal anything? Well, in our case with our z versus t graph, this would just be z times t. Now, z times t, of course, you are not going to find back here because we made up z. However, if this were instead a velocity versus time graph, then velocity times time, does that equal anything? Well, let's go in, check your PRT6, and let's see if it does. Does this equal something? Well, velocity times time, cross multiply right here, oh, that would be displacement. That does equal something. And in fact, if it equals displacement, and that's what they want, guess what? Back up and do the area. That's not that hard to do. You did this earlier in the course. So this was, for the first 4 seconds, you would just do this shaded area. 1/2 base times height. So the base is 4, the height is 10. 4 times 10 is 40. Half that is 20. That's it. Of course, you'd have to go with the units with that as well. If it is not on your reference table, sometimes it won't be. For example, d times t, the area of a d versus t graph, is not on here. Does it equal something? Yes. Is it in our course? No. So if it's not here, well, now you've gotten down to essentially your last option. The very last option, which is rarely used. In fact, there's really only one context that we use it. Your roof, your rise plus fall. Well, that's available to you if you need it. So, here, your very last option, and here's the only place it shows up, so I'm going to phrase it the way it's phrased. What is the total distance over some time period? So from, let's do the entire time interval. Over the total time. And this will be on a displacement versus time. And I mention it here just because this is the only real place you use it. Okay, so what is the total distance over the total time on a displacement versus time? Well, if you've tried all the others, you tried the direct read, it wasn't on the axes. You tried the slope, you did your y label over your x label, that didn't match up to what you wanted. You tried your area, the y label times the x label, checked the PRT, that didn't work out to what you wanted. The only thing left is your roof, your rise plus fall. My orientation is rising and falling as we speak. Okay, so our rise plus fall. Move over a little bit here. Okay, well, how do you do rise plus fall? The only real place we use it is with displacement versus time, and that is simply all of the upward movement. This is all on the y-axis, plus all downward, also on the y-axis. Movement maybe is the wrong word here, but anyway, all upward and all downward from the y-axis, add them together, you'll get it. So the example here would be, how much rise do we have over the 24 seconds? Well, we've started out at the 0, and notice that it's gone, I'll go here in the middle, it's gone up, 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 till it hits this peak. Now there's a pause in between, but this is a rise, pause, rise. We have a rise of 20. Then, from that same peak, we have a fall, 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 all the way down to 0 of 20. The rise plus fall would be 20 plus 20. Call it all positive, you get 40. If this were a displacement versus time, the total distance would actually be 20 plus 20, 40 meters. So, there it is. There's Dr. SARF, quick version. And Dr. SARF will basically cover all of your kinematic graph questions. Now, things can get a little more wordy. When is the motion east? Well, this goes back to your basic definitions, where you say, well, what does motion mean? Motion is actually velocity. East, what does east mean? Well, you defined at the beginning of the problem, perhaps you defined east to be positive. So really, motion east might mean, when is the velocity positive? And then you back up and say, what kind of graph is this? How do I get velocity from the graph? And this takes time to master, but if you do it, there's no more memorization of, oh, the slope is always velocity. No. The slope of this graph is velocity. Slope of the other graph is something different. You don't need all that. You just need Dr. SARF, and you need sharp definitions. You gotta know motion means V. You gotta know when there's direction, you define it positive or negative. You have to know slope represents, area represents, and then go look it up on the reference table. You have to know the direct read luces, where the change is the final minus the initial and the average. Add them up, divide 2, which works in Regents physics, but beware when you go on to AP. By then, hopefully, you'll know what's going on anyway. So this Dr. SARF really does cover all the situations. Replace Z with V, boom. Replace Z with V, boom. Replace Z with A, boom again. And so now, your actual assignment is to do exactly what I just did, except you think it through. Don't bother copying it, that's a waste of time. You spend some time on this page, think it through. How do I generally approach it, each of these? And then what does it mean for each of these? Notice, it could come out to mean nothing in this course, that's fair game. And we're not gonna do rise plus fall with your velocity and your acceleration graphs. It's not something that makes sense there. It really only works on your displacement graph. Displacement, it works on distance too. Okay, so that essentially covers what you need to do. And so, while you let all this here simmer in and sink in, take you out with a little bit of motivation. Tell him, Dr. SARF.
Sun is down, freezing cold. That's how we already know.